Good morning, everyone. Thanks for giving me the floor. I'm Sadman Jashim Sakib. Our topic for the conference is Virtual Teaching Assistant for undergraduate students using natural language processing and deep learning. Every day, the popularity of online education is growing because of COVID 19. Many universities are integrating in person and online education systems, which is insufficient and affects the students by decreasing their retention rate. So, keeping those points in mind, we are proposing a virtual teaching assistant bot along with its primary dataset and its system architecture in this paper. We are also showing an initial implementation of the proposed model, which is an AI chatbot that can respond to the student's query about Python programming language course. NLP based assistive chatbots are utilized in the health industry, e commerce, banking, food tech, and more. 1.4 billion people use chatbots, which decreases operating expenses by 30%, and 27% of smartphone users are interested in AI support systems. The education system can employ chatbots, especially for interactive learning. There is an opportunity to use chatbots to support students. There are already some existing systems related to our work for assisting students for different courses all over the world. For example, Ashok Goel's Introduction to Jill Watson is the most relevant literature in our study. The virtual teaching assistant Jill Watson relieved teachers from answering students' questions about the course knowledge based artificial intelligence, but it was not a personalized system. Again, virtual teaching assistant ProTracer 2.0 compares students' answers to this teacher's solution to measure accuracy. Some literature related to our work are available like Pythonbot, Progbot, eJava, and Coding Tutor. All of them are mostly focused on one programming language. As there was no dataset available for the fundamental Python programming language, we had to create a completely new dataset for this course. At first, our objective was to create a flowchart of our work plan. As you can see in the figure, we started a sample collection accordingly. At first, we chose 10 books for the course, which was we were inspired by. Then we formed a group of 2 members to choose books from among them. After selection, the whole group evaluated the books and agreed to gather samples. Next, we assigned the topic selection task to each of the member of the group. We initially compiled a list of chapter specific topics, then we eliminated all repeated and redundant topics and compiled a list of unique ones. These topics encompass the entire course. One of the hardest tasks was to select questions and answers. So after that, we distributed the unique topics to each of the members, and each member compiled all potential questions and answers for each topic. The process of tagging the question was one of the most challenging aspects of this study because arranging the questions according to a similar pattern appeared to be perplexing. We gave a tag to every similar patterned questions. Next, to verify the completeness of the data we obtained, we consulted a teacher's assistant of this course. According to the feedback we received, we modified our data set and we included several essential questions acquired from the students' queries to our dataset. After fixing all the errors in the dataset, we finally obtained our desired dataset. Our Python programming language data collection is organized hierarchically. The root is set to intent. We save topics inside the intent. Each topic includes tags. Again, each tag comprises questions of similar kind, and lastly, each question corresponds to a certain response. Currently, our dataset has total 214 unique tags and 1006 questions and 254 unique responses. In this figure, you can see 18.7% of all tags have 2 or less questions. 18.2% contains 3 questions. 22.4% of the text contains 4 questions, and the remainder contains 5 to 10 questions. So we can say on an average, each tag comprises between 5 to 6 questions. We perform some data preprocessing techniques on the dataset, which include case folding, punctuation removal, removal of stoppwords, stemming, lemmatization, emoji removal. After that, our dataset is ready to be trained. For training, we took 80% of data, and training data will help to train the classifier models on the basis of which pattern fall into which tag, and rest 20% part of data will be used for testing the accuracy of trained classifier model. After all the pre-processing, we must evaluate how efficient and balanced our dataset is. So, to determine this, we utilized four distinct classifiers and compared their respective accuracy gains. After evaluating the accuracy, we will be able to predict the accuracy of the neural network model of our prototype. Our chosen classifier for training and testing are the naive-Bayes classifier, the decision tree classifier, the linear support vector machine, and the logistic regression classifier. After training and evaluating the models with the entire dataset, the accuracy for naive-Bayes classifier was 21.42%, decision tree classifier was 58.67%, linear support vector machine was 50%, and logistic regression was 62.24%. Again, since we were not entirely satisfied with the overall accuracy of the entire dataset, we omitted certain tags with less training patterns and refactored the dataset while preserving the patterns of tags with at least 10 patterns. On rerunning these classifiers on the refactored data, the accuracy of each classifier improves. Now the accuracy of naive-Bayes classifier became 66.67%, the decision tree classifier was 75.75%, linear support vector machine was 69.7%, and the logistic regression became 75.75%. So to get a clear idea, we rerun all four classifiers using a more refactored data set to determine if eliminating tags with fewer patterns yields a substantially higher precision. So now the accuracy for naive-Bayes classifier is 73.91%, the decision tree classifier is 78.26%, linear support vector machine is 86.95%, the logistic regression is 82.6%. After testing the accuracy, we can anticipate that the neural network of our prototype will have the accuracy of more than 90%. Our goal is to increase the accuracy of the entire dataset in the future by incorporating additional patterns for each tag. We test our four classifier on the entire dataset and obtain an average F1 score of 0.16 for the naive-Bayes classifier, 0.56 for the decision tree classifier, 0.46 for the linear support vector machine, and 0.6 for the logistic regression. When we finally retest all four classifiers on our more refactored dataset, we obtain an average F1 score of 0.71 for the naive-Bayes classifier, 0.82 for the decision tree classifier, 0.85 for the linear support vector machine, and 0.81 for the logistic regression classifier. Now I'm going to talk about the prototype implementation steps, which includes NLP techniques, the neural network model, the model training and testing and result, and lastly demonstration of the prototype. We cannot just feed the input phrases to the neural network in its existing form. We need to translate the pattern strings into numbers that the network can interpret in some way. This is accomplished by transforming each statement into a bag of words. To do this, we collected training words or all the terms in the training data that our VTA bot can look at and generated an array named all words. The bag of words for each new sentences was then calculated using all of these keywords. We used two more natural language processing techniques, which were tokenization and stemming. Now, a multi-layer feed-forward neural network consists of neurons that are ordered into layers. The first layer is called the input layer, the last layer is called the output layer, and the layers between are called the hidden layers. So, a feed-forward neural network with hidden layers is used to create our neural network model. Training and predictions are the two modes of this, supported by this feed forward neural network we used. The two datasets are required for this training and prediction of this neural network: training set and test set. It takes the input, passes it through various layers one by one, and then finally generates a probability using softmax function. We created the training pipeline, which consists of multiple sequential steps that do everything from data extraction and preprocessing to model training and deployment. We split the dataset into 8:2 ratio. For training and testing, we set the batch size to 8 and the number of epochs to 1000. We calculated the loss in every 100 epoch. We calculated the accuracy in each 100 epoch. In the first figure, we can see that the first iteration, the loss was 1.1089. After our training concluded, our loss was effectively reduced to 0.00007. Again, in the second figure, we can see the accuracy also increased to 95%. Now let's watch the demonstration of our video bot prototype. Here we can see our VTA bot is responding to the queries related to fundamental programming language of the students. After deployment, we intend to refine and improve the model using knowledge extraction to monitor student and VTABot interaction. We intend to add student engagement by analyzing students' behavior. The VTABot will be able to tell which kids are struggling and which are unhappy or upset. If it detects, then it will act proactively and send a warning to their respective lecturers. Our course options will be expanded soon. Current study focuses on personalizing learning materials based on the students' interaction with the VTABot. So, to conclude, in a nutshell, we can say students are sometimes hesitant to contact with the strangers, and due to the newly established online-based education system, they get disoriented when transitioning to new programming concepts and lack adequate supervisions. Our goal in writing this paper was to introduce our VTA bot as a medium of learning to make their educational experience more enjoyable and reduce their chances of failing. Along with answering core Python programming questions, our VTA bot will be able to assist students with course-related concerns and provide real-time assistance from their teachers. To help students even more, we intend to continue working on improving our system in the years to come, hoping for a revolution in our education sector. Thank you, everyone. Thank you so much for listening.